We will start with a postdoc from Columbia University in New York, which is Zhaoran Zhang, and she will start right now.
Hello, everyone. My name is Zhang. I'm from Columbia University. Today, I will talk about the differences in learning strategy in a simple virtual task and a real task. Virtual environment has been widely used in studies in motor neuroscience. One typical example is reaching movement on a horizontal plane. Subjects usually see a virtual representation of the task and their hand movement on a virtual screen. And the haptic feedback usually provided by joystick, robotic manipulum, or sensing gloves. If you compare to the reaching movement to the real world, we find that the simplified virtual tasks have fewer degrees of freedom to control. Also, the movement is constrained on a 2D plane instead of in a 3D space. Virtual environment has also been used in rehabilitation to create motivating games for patients to practice. However, there are studies suggesting that the transfer of the motor skill from virtual environment to the real world could be problematic. So we're asking the question that, do the findings in virtual environment can scale up to realistic behavior? We use a same task precisely matched in virtual and real world and to test the performance and their learning strategy. The task we use is a target-oriented throwing task. The idea is from a British pub game called Skittles. There's a post in the center, a bar attached to the post, and we reduce the target to 1. The task is to throw the ball and fly around the post to hit the target. We render this game into virtual environment. Subjects see a top-down view of the task. This is the post, this is the target, this is the bar, and they put their forearm on a horizontal manipulum. On the tip of the manipulum is a wooden bar. And subject also see the map of their forearm movement by this purple bar. The grasp and release of the ball was controlled by a pressure sensor attached on the wooden ball. So subject will throw the ball and let it fly around the post. The goal is to hit the target with the ball, and if the target's hit it will turn from yellow to green. The performance error of this task was determined by the minimum distance between the target and the ball trajectory. And this was decided by the tangential velocity and direction of the velocity of the ball at the moment of release. If we calculated the error with all the possible combinations of release velocity and release angle, we can create this solution space, error here coded by color, and then we can use a single dot to represent a single throw. The green line here indicates all the combinations of velocities and angles that can hit the target. We call this solution manifold. This is a redundant task. That means any combinations of angle and velocity on the solution manifold can hit the target. For example, the trajectories 2 and trajectories 3. We also did this same task in virtual environment. We attach markers on subject's body, on the bar, the post, the target, and we precisely match the physical parameters in virtual and real tasks, including the ball mass, the height of the post, the length of the string, the position of the target, etc. And then we use 12 motion capture cameras to record the positions of the hand and the ball trajectories. To match the equation, to match the physical models and the matrix of the virtual and real task. For the virtual task, we first transform the angle and angular velocity of the manipulum to the tangential velocity and angle of the bar. And for the real task, since the post is high enough, we ignore the third dimension and only use the X and Y position. And we use the same physical model as we used in the virtual task and successfully recreated the bar trajectory by with the estimated angle and velocity. And the estimation error is around 5 to 11%. 16 subjects were recruited and divided into 2 groups. Each of them practiced 4 blocks of 30 trials every day and continues for 3 days. Let's first take a look of the success rate or hitting rate and average error. With 3 days, 12 blocks of practice, both groups is getting better and getting lower error. The virtual tasks have higher error, especially at the beginning of the practice, but at the end of day 3, the virtual performance catch up with the real. So that means the virtual task needs more practice to be successful compared to the real task. Besides the simple measure of hitting rate and performance error, we also analyze the variability in release angle and velocity. Here we find from the early practice to late practice, the data cloud is getting closer to the solution manifold, which is the white line. And also it's lie along with the solution manifold with practice, and also the dispersion of the data cloud is shrinking. Similar variability changes can be found in all 8 subjects of the virtual task, although they choose slightly different place on the solution manifold since the task is redundant. Similar findings can be observed in real tasks. The only difference is in early practice, real task is closer to the solution manifold compared to the virtual task. And you may notice that although we constrained the release positions for the real task, subject can choose slightly different place to release their bar, so they have slightly different solution spaces, but the solution spaces is quite consistent within one subject across practice. To quantify this variability changes in performance, we use a variability decomposition method called Tolerance-Noise-Covariation or TNC framework. So imagine here is a data cloud in early practice on the solution manifold. How to get this performance better? There are 3 things we can do. First is relocating, that move the center of the data cloud to an area on the solution space that error is not very sensitive to the changes in release angle and velocity. We call this tolerance cost or T cost. T cost decrease at very early in the practice and remain lowest through the practice. A second thing we can do is make the variability lie along the solution manifold, that any change along the solution manifold won't affect the performance error. We call this the covariation cost or C cost. C cost decrease lower and remain higher compared to the T cost. The third thing we can do is reduce the dispersion of the data cloud to make it getting closer to the solution manifold. We call this noise cost or N cost. N cost decrease at the slowest rate and remain the highest across practice. Those findings, those trends of cost decreasing were found with previous studies. We applied this TNC analysis on the virtual and real task compared to a previous virtual surrounding task with a different target location, which means different solution space. They all share the similar ranking order, that N cost is the highest, while the T cost decreased fast at the beginning and remained the lowest. The same rank order has been found in other learning tasks in a virtual voice-controlled task. So the similarity between virtual and real task here showed that although the movement are so different in the virtual and real task, but they share the similar learning strategy. Next, we separately compare the T and C cost in virtual and real task. What we find is for the real task, the virtual task, for the virtual task, the T cost is very high at the beginning compared to the real, and the N and C cost does not have significant differences except the first block of practice. So then we can suggest that the high performance error at the beginning in the virtual task is mostly induced by the T-cost, which means in the virtual environment, subject needs longer time to explore the solution manifold and to find the best strategy. So in conclusion, the virtual tasks require more time to practice compared to the real task, although they reach the same level of performance at the end of day 3. Despite there's higher degrees of freedom to control in the real task, it still did better than the virtual one. And then we think, what is the reason of that? One possible explanation is in the real task, although we instructed subject to only release the bar at a certain area. However, they can still choose a different place to release that modify the solution manifold. Maybe they can take advantages of this changing in solution manifold to control the task better. So back to the question we asked at the beginning, given the widespread use of the virtual environment in motor neuroscience, our results raise some caveats for unreflected generalization of those findings from the virtual environment to complex real-world actions. Virtual environment may present initial hurdles that need more time to practice to find the best strategy. So cautious need to be applied to the basic researchers in motor control and also in rehabilitation, that the simplified setting in the virtual task may not scale up to realistic behavior as expected. So I would like to thank the co-author, also my PhD advisor, Dr. Dagmar Sternad, and the Action Lab at Northeastern University. I would also like to thank my current postdoc advisor, Dr. Daniel Walpert, and the sensorimotor learning group at Columbia University. And thank you, and I'd like to take questions.
Okay, thank you for this very interesting presentation. We have now time for questions. We have one already in the Q&A chat.
Okay.
It's from Katinka, and she is asking, she or he, sorry, is asking, why did you use a 2D representation on the virtual task instead of a 3D rendering of the task?
Yes. So previously we've done a lot of previous work on this virtual 2D throttling task, and there's a lot of findings from the virtual throttling task. However, then we have that question, does this finding with the virtual environment transfer to the real? So we decide to replicate exactly the same thing in the real. So because we previously first have this, and also with the 2D version, subject can have more precise sensory feedback. They can precisely see how much is the performance error compared to a 3D setup. It might not be that clear how close the bar is to the target when throttling.
Okay, we have another question from Zhaoran, asking, why do you assume more exploration in the virtual task as the exploration space is much smaller in virtual than real throwing?
Sorry, can you repeat the first part of the question?
You can also read it in the Q&A part, but is why do you assume more exploration in the virtual task as the exploration space is much smaller in the virtual than real throwing?
Yeah, so the main reason is because the virtual tasks have higher T-cost. So the T-cost indicates the data cloud is relocating from the beginning to the end. So that means in the virtual task, subject explore more around the solution space to find the best strategy compared to the real one.
Okay, so we have time for maybe one more question if anyone in the audience wants to jump in. If not, we will thank you for your presentation and we'll move along for the second speaker.